So in this class, we'll talk about the first lecture in this course, basic concepts of digital signal processing or basic concepts of DSP. Let me check. Okay, there's the transcript is there. It's not a big deal, but I want to make sure that it is recorded. I believe it is. All right. Okay, start slideshow from the beginning. Display settings, duplicate. All right. So what is digital signal processing and what is the advantage of digital signals over analog signals? Basically, digital signal processing will be dealing with digital signals. Digital signals have values of zeros and ones. So we represent the signal in the digital form. So it's either 0 or 1, or what we call binary signals. And sometimes these zeros and ones, we make codes out of them. Today in the class, we'll talk about encoding. So let's say, for example, I have the sequence 0, 1, 0, 0, 1, 1, for example. I can group these numbers. So this one will have the value 2, and this one will have the value 3. So I give a 3-bit sequence a number. That's what we call encoding. And so we have the signal represented in digital form, and it will be processed using a digital processor. Now, the good thing about digital processors, they are fast. So that's one thing. And usually, let's say some filters or some operations could be done with software. So I don't have to change the hardware every time I need to change the specifications. So for example, if I'm dealing with the filtering, let's say I have this low pass filter. Probably if I want to do some modifications, if I'm in the analog domain, I need to play around with R, C, L values to work out a suitable design for this filter. So there will be some hardware. But with digital filters, so that's the analog. And with digital, the hardware remains the same. It's like dealing with the chip, but I'll be changing with the code, with software. Now, what is a signal? Signal, anything that carries information, from basic signals like a smoke signal into voltage and current signals that could be represented in different ways. So the signal could be considered as a pattern of variations of physical quantity. In our case, it's either voltage or current that can be manipulated, stored, or transmitted by a physical process. So we have audio signals, speech, which is a kind of form of audio signals. We have images and we have videos. Images, we have it like a matrix. Hopefully, after you pass this course, there's a course of audio and image processing. Like the first part of the audio and image processing will be just the regular DSP, like about 2 to 3 lectures. And everything will be an image processing dealing with matrices. Now, videos, basically, it's just a stack of images, but we add a third dimension, which is basically the time, like it's frames. Now, each image will be considered as a frame. In this course, we'll be dealing mainly with one-dimensional signals or audio signals. Now, signals can take many forms of representing, like speech signals can be converted to electric signals through a microphone, then can be also converted to numbers using the audio processing. So the microphone receives the vibrations of air because of the sound of the voice and change that form into a digital signal or electric signals. And this is what we call actually a transducer. Transducer is a device that just changes the energy from one form to another. So a microphone changes the energy, like the voice vibrations, into electric signals, and can also be converted to numbers using audio processing. So everything in the computer will be numbers, 4, 5, 6, whatever. But these numbers also go back to the basics. They are digital numbers, zeros and ones. So this is just definitions about digital signals in general, and what is digital signal processing. So this is a typical form about what happens when we deal with a microphone. So the speaker sends speech, let's say is giving a speech. That voice is just vibration in air. And there are some materials here, I believe is made of carbon. The vibration of air will affect the material in here. There will be vibrations in the material, and that will convert the signal into an electric signal. Then we have a device called analog to digital converter, ADC, analog to digital converter. That device basically changes analog signals into a digital form through the process of sampling. We've done sampling before. So once we have sampling, we do a quantization, giving these samples a quantity, a certain quantity. Then these quantities, these values will be processed through the digital system, usually a chip, part of a computer, like do some filtering, do some amplification, many other format. And then you are ready to send it back for, let's say, human use. So you have the digital signal, use a digital to analog converter, basically the inverse process of here. And then you have the analog signal that you can send it to a speaker. So that's a typical example. That's the voltage N. That's what, let's say, the output of the speaker. That's the electric signals. And here is the output in the digital format. And this is what we call quantization. We'll talk about it later. Quantization. Basically, my signal is having infinite, let's say, set of values. Now, this set of values, I can decide I want something like this. So let's say I have 5 levels or 4 levels, or I can have more levels. And the more levels, the better accuracy I have. But the more memory I need. We'll talk about it later. Okay, so some history about DSP. So the origin of digital signal processing can be tracked. So it goes back all the way to the 17th century, like when numerical differentiation, integration, and interpolation methods were developed. So basically with the advancement of calculus, differentiation, integration. Now, with the evolution of computer, definitely the evolution of DSP has increased. So in the 1950s, we have digital computers and initial application and the simulation of analog processing methods. So whatever, like the main process or the main need of computers is kind of simulate what's going on in the analog domain. Now in 1960s, DSP kind of become like matured and start to have its own field by itself. So initially it was part of the computer field, and then digital signal processing has become its own field. All right, so digital signals, we talked about it. It has only values, zeros and ones. So a digital signal is a signal that represents data as a sequence of discrete values. Now, these values indeed are zeros and ones, but 0 has a meaning and 1 has a meaning. So 1 means that's a logical, an analog 5 volts. That's a logical 1. And you have a 0 volts, that's for like logical 0. And usually you have like there is a threshold. So sometimes a certain receiver, the threshold is usually 2.5 in this case. So if the signal was received 4 volts, 4 volts, that means it's a logical 1. It's above the threshold. So it will be considered as logical 1. If it's less than 2.5, like 1, it will be considered logical 0. So that's what we mean by zeros and ones. Like I'm not sending an actual value of 1. It's actually a voltage. Is 5 volts. So this signal can take only one value from a finite set of possible values at a given time. So it could be either 0 or 1. With digital signals, the physical quantity representing the information can be many things: variable electric current or voltage. As I mentioned, with the 0 or 1, I'm meaning 0 volts or 5 volts. That's how the computer reads things. At the end of the day, it's just electricity. You're dealing with electricity. Now, signal processing can be divided into 2 main domains. We have digital signal processing, which is the core of the course. Analog signal processing, let's say as an example, modulation. some filtering with RLC and stuff. So there are some work on analog signal processing, especially in telecommunications, but there's also like a huge demand in digital signal processing. And our focus of the course is in digital signal processing. So usually DSP systems consist of these main components. So you have an analog input, and this input will pass through a filter. And we'll mention the use of let's say, the importance and the use of this filter. Now, the output of this filter is something what we call a band limited signal. Basically, usually signals, let's assume I have a signal with a certain frequency response, this one. So this is like assumed like it's an ideal case that I say my signal is band limited. But always keep in mind there is something called noise. That's always present in many systems. And the noise span over all range of frequencies. So to make sure that I'm focusing on the desired signal, I usually apply a certain filter to the signal before doing any processing. And that's what we call a band limiting filter. And that's what the analog filter is, a band limiting filter. So one reason to eliminate noise. Another reason is something in sampling theory. So assume that I have a signal here that has the same response I did there, and I did sampling. So basically I have a train of pulses. Okay, in sampling happens in time domain. So I assume that I have a certain frequency of certain analog signal, input signal, have something like this. This is the signal. So samples, I just multiply it by a train of pulses. So this is sampling. Now in frequency domain, this sampling that I have an input signal multiply with pulses. I have the same signal, that's the signal frequency domain, but I'll do convolution with another train of pulses. And this will lead to something like this. That's something called echoes of the signal. That's a frequency domain. So this is the frequency, and this is frequency. This is time. Actually, to draw it in more accurate way, I have the signal in time domain. I multiply it with a train of samples. So this is sampling. So I'll get these samples, these points in time. And samples are integer values, 1, 2, 3, like first sample, second sample, third sample, fourth sample, and so on. So this is in time domain, you multiply. If you remember in signal systems and Fourier theory, that multiplication in time domain will lead into convolution frequency domain, and the opposite, convolution in time domain will lead into multiplication into frequency domain. So I have multiplication in time domain, that's the sampling. In frequency domain, it will go into convolution. Now this signal, I assume that has this response, and the train of pulses has, like in the Fourier transform, it's again another set of train of pulses, however with different amplitudes. Now when you do convolution, when you convolve with a pulse, you get the same signal. If you remember f of t convolved with delta of t minus t naught equals f of t minus t naught. So you get a shifted version of the signal. Same thing applies when you have it as a function of frequency. Okay, I used f here, so let's call it x. So x of f convolved with delta of f minus f naught equals x of f minus f naught. So this is in time domain, and this is in frequency domain. So it means that if I'm convolving a function with a shifted delta, I'm going to get a shifted version of the function. So here I have this one. That's my first delta. So I'm getting an image there. Now this is second delta, another image. So basically I'm making replicas of this response here. Now, why do I need the band limited filter? I want to avoid aliasing. I don't want all of these images to pass through my system. I only want one image. So that's why we need the analog filter, the band limiting filter to remove these other images. Otherwise, there will be some phenomena called aliasing. We'll talk about it later. Now, once I have my band limited signal, I send it to an analog to digital converter through the sampling. Now I have the digital signal, apply the DSP, like most of the theory in this course. We will not worry about all these objects here. All I have the input signals. I'm going to give you the response, the numbers, and you just need to do the math. You just focus on the math part. Also, this part here, you don't have to worry about the digital to analog conversion and send to a reconstruction filter and so on. Our core, let's say, the core of the course is just the DSP part. All right, advantages. You don't have to memorize them, just to show you that DSP has way more a set of advantages when compared to analog signal processing. So performance of DSP does not drift with temperature, age, or other external effects. As I mentioned, it's software. The performance of the DSP system will not be affected with temperature. If you guys remember transistors, beta, what do you call it, the amplification coefficient of the transistor, the BJT. Actually, beta here, it's like for room temperature, 25 degrees. If the temperature is 50 degrees, like this whole thing will change. And then the whole characteristics of your electronic system will change. However, in DSP, there is no issue. So it will not drift, like the performance of the system will not drift with temperature, and it doesn't matter how old the system is, the performance will always be the same. So it has a stability. By here, stability doesn't mean that it like give you overshoot or something. It's consistent. Like the performance will not vary through time. It is reproducible. It's the same performance. Again, if you deal with 50 degrees or 50 degrees, doesn't matter. You always have the same performance. It could be obtained from unit to unit since there is no variation due to competent tolerance. You have exact values. Also, in analog values, if you remember, even the resistor usually have like 100 ohm plus minus 5%. The tolerance. Tolerance is always something that comes with analog. In here, there is no tolerance. It's always exact value. You determine the values you need. And you're gonna say, oh, I designed a filter and the bandwidth is 50 kilohertz plus minus 10%. No, that doesn't happen in DSP. In analog, yes, because there are some variations because of temperature, age, etc. Now, this is the biggest advantage of DSP, software implementation. Most of our filter design will be software, just codes in MATLAB. Or could be any other language, but MATLAB is the most, let's say, user-friendly when it comes to DSP applications. So if you want to change any characteristics of your design, you just change numbers, like in your code. You don't have to bring components from somewhere. So DSP can be implemented using software on a computer, and it's easier to build and test. So there's a flexibility. Again, could be easily programmed and reprogrammed to perform variety of functions. We have the advantage of using digital electronic circuits, integrated circuits, digital ICs. So advanced semiconductor technology made digital ICs smaller, cheaper, more power efficient, and faster. Like nowadays, we speak of gigahertz like it's nothing. Like your processors, 3.4 gigahertz, that means 3.4 billion operations per second, which is a lot. You guaranteed accuracy. Again, there is no tolerance. Everything is exact. You can reproduce values the way you want, and the accuracy can be achieved simply by adjusting the number of bits. Realization of functions not possible with analog signal processing, like linear phase response or adaptive filtering. Let's not worry about these concepts, but it's saying that there are more things that you can do in digital signal processing when compared to analog signal processing. All right. However, like there comes some disadvantages. Memory usage. If you want high accuracy, you need more memory. It's kind of complex. The level of math is a little bit higher in level when compared to analog signal processing. So also that you need to add pre and post processing stages, the analog digital converter and digital to analog converter. All right, and yeah, bandwidth, DSP or digital signals in general require more bandwidth compared to analog. So there's also cost limitations, and that kind of makes sense. Like when you want high performance, you have to pay for that. So when large bandwidth signals are involved, fast analog to digital convergence and digital to analog convergence are either too expensive or do not have sufficient resolution. Power requirements, they always require electrical power due to the use of active devices, transistors, ICs, op amps. Though they sound like analog, but they have applications in digital. Okay, now another important thing here, due to quantizations, like there's some error. Again, you don't have always the exact value. So let me draw this graph here of a signal, something like this. And let's say I'm going to use only 2 bits. Now, how many values can I get of 2 bits? 2 to the power 2, that's 4. So I can have, like, let's assume this is my first level, second level, third level, fourth level. And I can only approximate to these levels. So let's see how sampling happens and how quantization happens. So let's assume I'm sampling in this manner. Something like this. Okay, so I did some sampling. Now these values have quantities, and these quantities come from the analog signal itself. So let's assume I'm having, that's from 0 to 5. Let me pick 4. 0 to 4. That's my values. That's my signal values. And my levels, I mentioned 4 levels. That's 1. I start from here. That's 1, 2, 3, 4. Okay, so that's my 4 volts. Or 3, since I started from 0. So that's my 3 volts. All right. So this value here is approximately, like 2 point something, right? Like this is 1, 2, 3. That's my analog volts. So here it's 2.25. This one is, for example, 1.2. This one here is almost 2.25. This one approximately 3.1. So those are my analog values after sampling. Now, when I use 2 bits, I'm restricted only to 4 values, either 0, either 1, 2, 3. So this one, 1.2, will be approximated into 1. This one only to 2. This one only to 3. And this one only, let's say, either 3 or 2. So that's what we call quantization. I'm giving these samples a quantity. Now, because of this, I'm getting an error. How to reduce the error? Increase the levels. So I have it like this. So I have now 3 bits, for example. And with 3 bits, how many values can I get? 8, from 0 to 7. So analog values are the same, but I have 7 levels. 0, half, 1, 1.5, 2, 2.5, 3, and that's it. Now I can approximate, like the first level, it's 0, 0, 0. Second level, 0, 0, 1. 0, 1. Okay, let's غير اللون. 0, 1. 0, 1, 0, 0, 1, 1. So that's the first 4, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Okay, so I'm having these 3 levels. So I can have better approximations. Let's say I have 0.5. Let's say, for example, I have 3.2. Okay, it's closer to 3. Let's assume I have 1.75. I can approximate it, or 1.7. This one is closer to 2, 1.5. There is a level there. So I can have it like, I can make a table like this: 0, 0, 0, that represents 0. 0, 0, 1, that represents 0.5. 0, 1, 0, that's a 1. 0, 1, 1, that's 2. 1, 0, 0. So that's the encoding part. So, oh, sorry, 1, 1.5. That is the 2. 1, 0, 1, 0, 2.5. 1, 1, 0, 3. 1, 1, 1. I skipped a point. 1.5, 2, 2.5. That's 3.5. Okay, so those are my 7 levels. Oh, 8 levels, yeah. So instead of restricting to only 1, 0, 1, 2, 3, I have 0, half, 1. So I have a value of 1.7 to the 1.5. The 1.5. So I have an error of 0.2. However, if I'm having only 2 bits, it's going to be closer to the 2. But I have an error of how much? 0.3. Now, if I have 4 bits, I have better resolution. 5 bits, I have 32 levels. 6 bits, 64 levels. So the more bits I have, the more levels I have, and the error will become smaller. So that's what we mean by finite word length. It could be 2, it could be 3, 4, whatever. So you have some truncation, you remove some values, and you have some round-off values, in addition to other sources of error like quantization. All right, so that's some disadvantages of DSP. However, these kind of disadvantages, when it comes to the advantages, you can ignore them. Nowadays with memory, like 4 bits are nothing, or 10 bits are still nothing. So requirements for DSP. So you have functional correctness. Sometimes when you deal with sequential behavior, that you need some set of correct inputs and outputs. And timing correctness, you have to be synchronized. Synchronized. Do you know what synchronized means? Like the sender and receiver, they have to lock at the same point. Like when you send the first sample, the receiver should receive the same sample, like in same set of order. So it means that appropriate timely response of the system to external events. Okay. Okay, so digital processing, we have seen that already. Analog, we have the analog to digital converter to get the binary signals. Now, if you want to go backwards from binary signals to analog, you need the digital to analog converter. So some examples of devices that use DSP, the digital camera. Nowadays, I think in your phone, that's a better example. You can take a photo, you can change the color, you can change the effects, increase the contrast. That's all digital signal processing. Another example, the scanners, the machines that you can scan papers. Some infrared imaging, let's say at night, this image will be probably look black, but with infrared, it detect heat, and you have a more clear image compared to optical images. Some microwave with the radar sensors to detect objects. Some resistive, I don't know what that is, but so that's again another example of digital. So again, that's another set of images. That's a function of distance, and that's another distance. So this looks like a satellite image, I would say, like an elevation model. That this is a high, like a mountain. This is a valley. It could be any example. Another set of images, X-ray images. If you deal with, let's say, inshallah, in the future, when you deal with deep learning, a lot of researchers have done COVID, like detection of COVID cases using these X-ray images. Like they train the model, like there are some features in the images, and the device, the computer will automatically itself determine whether this patient has COVID or not. Also, these kind of images at the airport to detect the dangerous objects. Ultrasound, check the health of the baby. MRI for the brain. And there are many, many more of applications of digital and image processing. Actually, they go together. Now, these are the steps of sampling, quantization, coding. Pretty much similar to what I did here. Hopefully, it will be more clear, let's say, if they have better graphs. So sampling, I think we've done that in signals and systems. So in DSP systems, first you need to sample your signal. So the first step in there to convert the input analog signal into a sample data signal, converted into samples, digital form. So you take samples at a specific instant of time, and this is what we call sampling. Okay, let me see. There we go. All right, so this is in time domain. So sampling in time domain, you multiply your signal, that's the X analog. You multiply it by the train of pulses, S of t. And they are separated by a constant Ts. That's what we call a sampling period. And they are equally spaced. So you don't have Ts, 3Ts, 4Ts, 10Ts. No, just by one value, Ts, 2Ts, 3Ts, and so on. So once you do the multiplication, you take samples at these points in time. So this is the first sample, that's the second sample, third sample, and so on. So this is what you will get at the output of sampling. Now in the frequency domain, I have multiplication here. It will become convolution and frequency domain. So this signal, let's assume the frequency response of the signal is something like this, and it's band limited. Band limited, I mean it has a minimum and maximum frequency. All right, and from the properties of Fourier, usually the Fourier transform is an even signal, like the signal is mirror image of itself. And the Fourier transform of these pulses will be another set of train pulses, now separated by omega s, the sampling frequency. Omega s equals 2 pi over Ts. So that's the relationship between omega s and Ts. Sampling period and the sampling frequency. Now, also the amplitude is 2 pi over Ts. That's the amplitude of each sample. Now, when you do convolution, basically this triangle here will have replicas centered at the sampling frequency or multiples of sampling frequencies. So at negative omega s, I have an image like this. Oops, something like this. At the center, I have an image like this, and so on. So you have these images. There you go, that's the output. Now there is a constraint. If you remember in signals and systems, to get good sampling, what was the relationship between the sampling frequency and the signal frequency? Like we said, the sampling frequency, Fs, should be larger than or equal. Okay, let me avoid this. Fs larger than or equal to Fm. And we did not talk why. Probably that was at the end of the course, and I think we didn't have time when we took the course. Now let's think of the rationale. Let's assume Fm is larger than Fs, or something like this. Or okay, omega s to have the same variables here, same thing. You just multiply both of them in 2 pi. Now if this one has a widespread like this, you will get this kind of response. Notice that there is some overlap happens between these replicas or these images. So the output will be having what we call aliasing. So in order to make sure that my signal, does not have aliasing, first, before sampling, if you remember in that slide, let me see, we have what we call a band limiting filter, band limited filter. So basically, I will make sure that the signal is band limited by applying a filter that has a cutoff frequency. You know what cutoff frequency? Cutoff frequency. You heard of cutoff frequency? Electronics, huh? Cutoff frequency. Basically, cutoff frequency that after that frequency, the signal will be 0. So you apply a filter with a cutoff frequency equals half the Nyquist frequency or the sampling frequency. So I will make sure that with sampling, I will not have aliasing. So I'll get something as close to this. All right. So yeah, when you have here sampling at twice the or larger than twice the maximum frequency, you'll get these spaces and there will be no aliasing. However, if you do not do that, or you don't have the, say, you do not sample at the proper frequency, you will have aliasing here, and this will cause a distortion in your signal. Like that will be the input of your DSP system, while it should be something like this. All right, so that's it about sampling. We will not do a lot of work on this one. You just need to know that you have to sample at twice the maximum frequency of the, at least twice the, at least twice of the signal frequency. All right, so some concepts here. So you need this condition. So that's the Nyquist condition. Omega S is the sampling frequency or the Nyquist frequency. And 2 omega m is the Nyquist rate. And omega m is the signal frequency. So when you have the sampling frequency larger than twice the signal frequency, that's what we call oversampling, and this is desired. Undersampling, definitely not, because that will cause aliasing. And critical sampling also is not provided. Usually you assume that the filter is not sharp enough, you have noise. Always sample at larger than the signal frequency, but by a bit, not exactly twice the signal frequency. All right, so we talked about anti-aliasing filters. So the main job is to make sure that the signal frequency response is within the, let's say, allowed range that is needed. So it's a low-pass filter with a cutoff angular frequency of omega c equal omega m, just to make sure that the signal frequency does not exceed this value. So it is used to band limit the input signal to avoid aliasing effects. To completely remove aliasing effects, such a filter must have ideal characteristics, or what we call a brick wall filter. A brick wall filter is like a brick. So it should be sharp and doesn't like has a flat response, etc. But this is impossible to realize or to design, let's say, to design. Several reasons. It's not causal, to require infinite number of coefficients, etc. So in practice, such characteristics are impossible to realize. We'll see later, like no matter how sharp or how much coefficients we add into the filter, we will never have perfect flat, and we will never have this like sudden transition from 0 to 1. Like they're always, usually filters will become like this. Let's assume this is the center. Okay, like this. Okay, whenever, or the best case scenario, something like this. And also there's sometimes what we call a ripple, like some response at the peak. So it doesn't matter what filter I use to reduce aliasing. This filter will distort some components in the pass band, like this one here, because it has some variations in the value, and it will pass some components in the stop band because I don't have the perfect transition, so it will pass some components, but to a certain limit that is acceptable. So it will have a finite transition band. So that's the transition band. So some of these effects can be reduced by oversampling. What it means that, okay, so my filter is not perfect, but I will not sample with omega s larger than 2 FM. 2 omega m, 10 omega m, and that will be acceptable in this case by oversampling. So for example, in telephone, a cutoff frequency is 3.4 kilohertz or 3,400 kilohertz. So usually if you want to apply Nyquist, you need 7.6 kilohertz for sampling frequency. However, they do sampling by 8,000 hertz, which is more by a bit. So instead of 6.8 kilohertz, they sample with 8 kilohertz, and it will do a fair good job. But sampling is carried out using a sampling frequency of 8 kilohertz rather than exactly twice, which is 6.8 kilohertz. All right, so practical sampling. So that's the title has nothing to do with the slide. Basically, the anti-aliasing filter, what we desire something like this, sharp, smooth, has a flat response at the pass band region and 0 at the stop band region. However, again, it's impossible to realize, impossible to design. So what will happen at the practical part? So I will have some non-flat output at the pass band. I have also some response at the stop band. That's the blue one. And there is this transition here. And these are the major issues what we have in the, let's say, realized or practical band limited filter. So yeah, there will be some distortion at the pass band. There will be some components from the stop band, and the transition is not smooth. Again, solved by having oversampling. Okay, quantization is used to convert the sample data, the discrete time continuous amplitude signal, what we gain from here, these sample data now give them some quantities into a discrete digital signal, a finite set of amplitude levels called quantization levels. As I mentioned, when you have 2 bits, you have 4 levels. When you have 3 bits, you have more levels. 4 bits, more levels, you get up to 16 levels. So the amplitude of each sample is rounded to the nearest level in the defined set. So there will be not like rounded to the nearest level, 1.9 approximated to 2 rather than 1.5. Now, one major issue is quantization is irreversible. So that's it, data will be lost. So there will be some loss, but to a certain extent. So that is quantization results in loss of information called the quantization error. So for a given sample, the maximum possible quantization error is Q over 2. Now Q is the what we call the spacing between quantization level or the quantization interval. There is a certain formula for that. I think it will be covered later. So Q is usually fixed because these levels are equally spaced. So we have uniform quantization. I think there are some other theories, but no, to the level of this course, it's always uniform quantization. So the quantization error can be reduced by either reducing the size of the quantization interval and increase the number of levels or basically the number of bits. So the maximum error you get is Q over 2, like the interval over 2. Basically, when you have 2 intervals like this, so this is Q. And the maximum error you get, let's assume a point cut exactly at the half. Because if this one it's in here, it will approximate to this value. This is my error. If it's here, this is the error. But if it was exactly at the middle, that's Q over 2. So that's the maximum error. So that's the maximum possible quantization error. Let's see if there's an example on this. All right. So let's assume in signal and time domain was something like this. So that's in time domain. Okay. Then we perform sampling. We got these points. How many levels I have? So that's 0, 1, 2, 3, 4, 5, 6, 7. So I have 7 levels. Okay, 7 levels, or probably 8 levels. So 7 levels, how many bits do I need? 3 bits. So I can say this is the level 0, 0, 0. This is 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0. There is 1, 1, 1 somewhere. All right, so when we do, that's the sampling. Quantization means that I can have quantities from these levels only. So for example, go to this sample, that's exactly at 0, 1, 0. This one, where it's closer to 0, 1, 1 or 0, 1, 0? This level here. So this is will be approximated like this one. This one here, you can debate here or there. Let's say it's going to be here. This one is closer to this level, or this level closer to this level. So it is approximated here. Now notice my exact values are gone. I have approximations nearest to the nearest level. This one here approximated here, this one here, here, and so on. So you have only these limited set of levels instead of having infinite set of values. Now I'm limited into these levels. So this one could be represented, that's 2, that is 2, that is 4, 5, 4, 4, 2, sorry, 4, that's 3, that's a 3, 2, 2, 3. And that's it. So instead of having, for example, this one is 4.6, it got approximated to 5. All right, so that's what quantization is. Is it clear? Sampling into quantization. So sampling, I have the samples with the actual values, but discrete point in times. Now quantization, I will have discrete point in time and discrete points in value. I'm limited with the set of values. Instead of having 4.6, I will have 5. All right, then coding. To be processed by digital signal processing, each quantized sample must be represented by a string of binary bits. For example, here I used 3 bits, so I'm having these levels. If I have 4 bits, I will probably have more set of levels. I can have like these points here at the half. And the more number of bits, the more levels I have, the less quantization error I may face. All right, so this string of binary bits called the code word, this process is called encoding. If we have L quantization levels, then each sample can be represented by at most log2 of L. So which is basically, if I have 8 levels, how many bits do I need? 3 bits, which is log2 of 8. If I have 16 levels, 4 bits. 32 levels, 5 bits. This is the relationship here. The number of bits is log2 of the number of levels. What if it was non-power of 2? What if it was 20 levels? How many bits do I need? Always use the number higher. So log2 of 20 could be 4 point something. It'll become 5. So I need 5 bits. Even if it's 4.1, it'll become 5 bits. So increasing the number of quantization levels, L will reduce the quantization error, but it will require more memory. Increase the code word length, which will lead into increase the storage and processing requirements. Now, the reverse process of encoding is called decoding. What they mean is, now I have these values in numbers. I have them the encoding part. Then I have the decoding. I can go backwards into here, which is kind of straightforward here. The coding, decoding, encoding, and decoding process is reversible. Because when I have 0, 1, 0, like for example here. So this one, I assume that this is 0, 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 0, 1, 1, etc. So I know that 0, 0, 1, that's the first level. I can give it the exact value. 010. So from coding and encoding, it's reversible. Initially, I have these values 2, 2, 4, 5, whatever, convert them to binary stream. Then if I have the binary stream, I can go back to the analog number 5 or 6. So coding, decoding, encoding, decoding is a reversible process. Okay, so here are some examples in real life scenarios, just for information, nothing to memorize. So when we deal with audio, the sampling frequency is 8 kilohertz. So how many bits are required? They are using 256 levels, 8 bits. For FM quality, it requires 12 bits. So you have 4,000 levels. Okay, there is no relationship, by the way, between those. Okay, but yeah, when you increase the frequency, they require more bits for sampling. For images, monochrome, when you have 8 bits, so you get 256 gray color values. RGB, 24 bits, 8 for red, 8 for green, and 8 for blue, because RGB images are 3-layered images. All right. Some other DSP applications, filtering and noise removal. Probably at the end of the course, we'll do a project on that. Speech coding and compression. And by the way, compression is one of the, let's say, good applications of DSP. Have you noticed an MP3 file and WAV files? Have you ever seen them? MP3, you know, it's like the audio files. Have you seen the WAV file? That's what we call like the raw audio or something. This could be 3 times higher in size. Let's say it could be, this one is 9 megabyte. The same audio in MP3 is 3 megabyte. It's compression. Megabyte. What other is in movies? AVI and MP4. So like all of them, yeah, they are extensions, but they are because of the compression. MPEG, MPEG, images, PNG, JPEG. So just you can look at these images. They look the same. They're exactly the same, but each one of them has a different size for the same image because of compression. Also enhancement. So some images like this one doesn't have much features. It looks dark. By doing some certain process called contrast stretching, you have, let's say, the same image but with more features, especially like the tree reflectance on water. Here it's like you barely see it. And there are more, like some of the applications like edge detection. You detect the edges in images. Even in audios, sometimes you detect anomalies in audios, and many more. All right, so that's it for this lecture, for the theoretical part of the lecture. If you want to have a break, and then we'll continue with the worksheet of this lecture. Just simple questions related to this, like in sampling, sampling frequency, domain. Yeah, I don't remember. Just a few questions, like we'll finish like in less than half an hour. So I want to have 10 minutes break. Okay, 10 minutes. 120. This timer here is off. So it's 112 now. 125 and 125. Okay, stop sharing. Okay, so for the other part of the lecture, share screen. So this is the worksheet I promised you to solve. It's already on Moodle. So using digital signal processing DSP techniques and to perform sampling the following analog signal. So determine the following. What must be the sampling frequency in order to perfectly reconstruct the original signal? So basically what we need is Determine the maximum frequency of each one. Let me see if I can crop this one. Snipping tool. Copy. Let's open the whiteboard. Control. All right. So for these kind of questions, basically we look at each signal I have. So I have two signals, and we'll look at the maximum frequency for each one of them. So here, the first one, 2 pi f equals 140 pi. But remember, sinusoidals are represented by a cosine or sine 2 pi ft plus theta phi, like for the phase. We don't worry about the phase for these kind of questions. So we look, and also the amplitude. Amplitude is not an issue for us, so just look at the frequency part. So each value here, 140 pi, that's equals to 2 pi f. All right, so pi and pi will cancel each other. So here for the first signal, the frequency is 70 hertz. Now the other signal here is 395 equals 2 pi f. So f in this case is 395 over 2 pi. Whoever has calculator, can you do the math for me? 62.86. So basically, this one has the maximum frequency, SFM. So in this signal, FM equals 70. So to have a proper sampling frequency, Fs equals 2 pi FM, which is going to be, 2 FM, 2 times 70, 140 hertz. So that's the sampling frequency to have a good reconstruction of the original signal. Nyquist frequency, it's just basically the sampling frequency, 140 hertz. The other part of the question is saying that repeated with these two signals. I think the idea is quite clear. Again, you ignore the phase, nothing to worry about the phase here, just a phase shift. You just look at this one here is going to be 120 over 2 pi, and the other one is 50. And I believe 50 will be the highest frequency in this case. So pretty straightforward, nothing complicated. No, it's just a phase change. Sine or cosine, that's a phase change. Okay. The third question, which is the last question. So a non-ideal digital to continuous converter takes a discrete sequence y of n as input and produces an analog output y of t according to the following expression here. Y of t equals from negative infinity to infinity n, y of n, p of t minus n ts. Now, where the time period is given to be 0.1 seconds, the input sequence is given to be the following. Y of n, 1 from 0 to 4, 0.5 n to the power, 0.5 to the power n minus 4 for the values from 5 to 9. Now, first part, plot y of n. So let me take a screenshot of this. Take the whole question. Copy. All right, so this is the expression that I want to draw. That's y of n. So I don't need this one actually. So I have this x-axis. I have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, up to 10. Okay, so it says that from 0 to 4, the value is 1. So that's 1. More or less something like this. Then at the fifth sample, 0.5 to the power 5 minus 4, that's to the power 1. So that's 0.5, something like this. Then at 6, so the only the power that changes, so 0.5 to the power 2, that's 0.25. And that's less, so it's going to keep decaying. And that's it, it will stop here. So this is 0.5, 0.25, 0.125, 0.625 or 625, and so on. All right, so that's n versus y of n versus n. Now for this pulse, p of t from negative 0.05 to 0.05. That's p of t. Determine y of t. Now there is one key point here that's saying that where the time period is given to be 0.1 seconds. So those are in samples in discrete. Now if I want to convert them into continuous time, so basically the samples here is what? 0.1. The distance from one sample to another is 0.1. Okay. Now if I want to do the convolution, because this one here, it looks like a convolution, or we can simply say y of 0 equals summation from negative infinity to infinity of n, n equal negative infinity to infinity, y of n, t of t minus nts, and t is 0 here, right? Y of 0. Or basically this one looks like a convolution. So basically I'm going to slide this one over the samples. So the first one, I'm going to have something like this. That's the first image. That's the second image. And so on. So it's just going to keep getting the same pulses. Because this one, if you want to draw it, is something like this. Negative 0.05 to 0.05. And the value is 1. And you're going to keep sliding it all the way to here. Yeah, it's not very accurate. I'll work on the key answer and send it to you later. But it should be, okay, so the amplitude changes actually. So this one is at this value here. This one here, this one there, like this. So it'll be something like this. So that's the signal, how it looks like in time domain. Yeah, it's not that it's a straightforward kind of question, but this is what we call a sample and hold. Like the reverse part of sampling or quantization. If you want to go back from digital into continuous domain, that's the usual process. So again, this is the first lecture, that's the introduction. The level questions will not be more than this. Next week, inshallah, we'll talk about finite impulse response filters and infinite impulse response. We will do plenty of operations like convolution, like the way we did in signals and systems. Let's see what other more. Yeah, we'll talk more details about filters and design of filters. And we'll also do some exercises in MATLAB next week. But yeah, that's it for today, just introduction. And if you have any questions, feel free to ask. If not, I believe that should be it for today.
Thank you.
Anytime. So let me stop the recording, stop sharing. Okay, one more record. stop recording. مش عارف مسكتني الحساسية بطريقة غريبة هاي.